So the work I'm going to talk about actually is directly related to some things that Piers was actively working on towards this latter part of his time. And just to elaborate, go ahead and get started. What we're going to talk about today is the carbon cycle and how it interacts with climate. And in particular, the ways in which the carbon cycle acts differently depending on where you are. And that creates a tale of three continents. We're going to use that to understand this very epic 2015 to 2016 El Nino period that just occurred. Now, one of the things to understand, and I'll go to the next step, is the organizing principle behind the carbon cycle is atmospheric CO2. And it's the increases of that atmospheric CO2 that's the primary driver of climate change. But there's a couple things I want to note. First is that it's going up. That's why it's causing a change, but it's not going up nearly as fast as it could. There could be a line, but that line is not there because the oceans and the terrestrial biosphere takes up roughly half of it. But it changes. And in fact, if you look at the seasonal cycle, you see the changes of productivity, the increased carbon or carbon uptake as the plants take on the extra leaves. Then you go into the fall, and then you go into the winter, it drops that. And the last thing is that the growth, how fast this goes up, varies from one year to the next. And that relationship is very much related to climate variability. And that's what we're going to look at. Now, the challenge is, in order to understand the way in which carbon dioxide is changing the global concentrations, we need to start looking at the details. And what you're looking at here is CO2 weather. And so the red values are where CO2 from the biosphere is increasing the amount of CO2 in the atmosphere. And what you see down here, is, for example, is blue, is where CO2 is taking it away. Now, you also notice that as we go through this seasonal progression, that you're seeing more and more red values up in the northern hemisphere. And that's because we're going through northern hemispheric winter. And that's where it's beginning to release carbon as plants decompose. But then, as we start going into the spring, you'll see that that starts decreasing. And then you'll start seeing those colors change as the atmosphere moves CO2 across, and you start seeing the uptake of CO2 as the spring starts and you start going into the summer. Now you start seeing, however, you'll notice that like in the tropics, you start seeing a very different story. You have changes sometimes where it's red, where it's releasing carbon, even while you're taking up carbon in the northern hemisphere. So we have to understand what are the different processes that are going to control that blue and that red. And so one of the things that we want to understand is the role of productivity, the role of decomposition, and the role of fire. And then when you deal with something like an El Nino, you might ask, which of those processes are going to become more important? So in that, we'll see that an El Nino has a particular flavor. In fact, with an El Nino signal, we're going to see the blue or the red. It's in fact going to be, it's the red. El Ninos increase atmospheric CO2 much faster than other parts of the year. So we want to understand why is it that El Ninos in particular would cause CO2 to go up much faster. So the first question we have to ask is, what is an El Nino? So what you're looking at here is the sea surface temperature anomalies from an El Nino, where you get this important atmospheric ocean phenomenon that leads to these increases in temperature. And that begins to propagate across, as we'll see as we go into August, and then we'll go into September. That tongue of temperature will come across, and it'll even come over here into Indonesia. And so the question is what kind of effect that has on things that you'd care about in the biosphere, such as temperature and water vapor. So in the sort of the June through August period, you see that in general, you have like dry and warm conditions. And then as you move further in time, we'll see a different progression where the teleconnections start changing where temperature and precipitation occur across the land. So you can really see here that during a typical El Nino, that Indonesia is sort of at the epicenter of those changes. And we're going to see, as a consequence, what those kind of changes happen here, as well as the dry and warm conditions that typically occur during an El Nino in South America, as well as in Africa. How do these patterns affect the balance of productivity, decomposition, and fire? We're going to use a number of different satellites to understand that question. The first one is the CO2 Orbital Carbon Observatory from NASA. This measures atmospheric CO2 columns, and is in fact sampling those kinds of signatures that we saw earlier on where we're looking at that CO2 weather. And you can see the variations that cut across, for example, in Africa. They cut across from the glint modes. We're also looking at fire from MOPIT CO, or combustion. This is carbon monoxide. And you can see as you progress through the different continents, you're having different kinds of processes affecting the carbon cycle. And then the last piece that we'll take a look at, the last clue, is going to be productivity. So this is solar-induced fluorescence. So these variations are changing or direct measures of photosynthetic activity. And the more they increase, the more you can see productivity occurring. Now that's not the only thing that matters. For example, the oceans still take up roughly half of the CO2. So we have to model and represent ocean carbon processes. So here you're looking at the eddies that are cutting across the oceans, and they're mixing in with different types of biology that together will define how much CO2 is being taken up from the oceans. And the last one, and perhaps the most important, is the fossil fuel emissions themselves. They're distributed over the world, and we use things like night lights in a data assimilation system in order to be able to understand specifically where is those fossil fuel emissions occurring. So the question is how you put all those pieces together. We use something called the Carbon Monitoring System Flux project, where we take surface observations, we put them into models that represent the terrestrial biosphere, the ocean, and the human activity. Those would then go into a chemical or an atmospheric transport model. In this case, is GeoSChem. And we use that to confront our predictions of atmospheric CO2 and CO against observations. Yeah, here's a signature. So we use all this together. So we put all this in this mix, and we estimate fluxes. And so what we did here is we said, okay, we estimate the fluxes, which is the amount of CO2 that's going into the atmosphere from these increases or the changes in the terrestrial biosphere. And so what you're beginning to see here is the increase as we go through the period of 2015, the changes in CO2 due to the change in 2015 against a baseline. And as you can see, well, as we'll see this sort of slowly progress, you'll see that the concentrations that we'll get from this signature, if you start adding them all up, would give you about 0.9 gigatons of carbon. That's the total amount. And that amount you can see beginning to propagate as it moves through the time. And what's very interesting about this signature, that concentrations start making their way down. You see they move across, they hit the Andes, and they'll start propagating down. Now, the carbon dioxide in that region, or the clouds, are really heavy, so it's hard to see it from satellites. But you can see down here. And so our inversion systems allow us to use the fact that CO2 is coming down here to back out what's going in there. By now using photosynthesis, we were able to determine those primary reductions in productivity rather than decomposition that was the primary driver of that 0.9 gigatons of carbon that was released into the atmosphere. If we move our tail over to Africa, we start seeing a different story. Now here we're now looking at the, again, areas and regions farther across to the east that the fluxes that we determined emit more CO2 into the atmosphere than our baseline year. And you can start seeing that what's going to be interesting about this is that we'll start seeing over time a seasonal progression of that CO2. Now, the amount of CO2 that was emitted in Africa at that time was roughly the same as the amount that was released in South America over the Amazon. Now, again, as you'll note, and so that amount was about 0.8, and you can see that this starts moving its way across towards the east, and we'll see as we start moving in our progression towards the very end that this CO2 signature, atmospheric signature, will start propagating westward as the temperatures and precipitation start changing. Now, the question we can ask is, what was the driver of that? Was that due to changes in productivity? Was it decomposition? Or was it fire? And in this particular case, we found out that looking at productivity and looking at fires, looking at CO2, there was actually decomposition, this accelerated decomposition that was the primary culprit in the increases in CO2 over Africa during that same period of time. So now we have two different continents, each one with a slightly different story. So we might ask, what about the third and last continent? What was going on there? All right. So last chapter, third chapter in this tale, is Indonesia.
The exhibit hall is now closed. Please
Now,
wrap your conversations
don't listen to them whatsoever. I never do.
and hall will reopen
Now, one thing about Indonesia
9:30.
is it's a very, relative to Africa and relative to South America, it's really small. But the amount of concentration, the amount of CO2 that's emitting from here is really quite large. In fact, it's roughly of the same magnitude as what we had for South America and for Africa. And the question is, what is the driver then of that very different atmospheric, or that atmospheric carbon signature? In order to do that, we used our observations of particularly Moppet, CO, which allowed us to show that this huge amount of CO2 coming from is largely from fires. And in fact, it was about 0.4 gigatons of carbon. The other part being reductions in productivity, because again, it's sort of at the center point of that El Nino signal. And you can see how that's propagating across these signatures that our satellites use, the unique signatures that allow us to infer what's going on here. This region is really driven by Kalimantan, and it's driven by peat that's being released due to unexpected or fires that occur. And that carbon's been sequestered there for thousands of years, and that ends up driving it. Now, the last piece about all of these is that when we look at these time series, such as this one, that was the second driest year out of 30 years. And the first one in South America, that was like the driest in the 30 years. So it seems like precipitation becomes a big driver. And overall, we see that the CO2 growth rate through this analysis was by and large came from the tropics. Not from the northern hemisphere, but from the tropics. The tail for each one of these contributions was about equal for each continent, but the reasons were quite different.
Wrap up your conversations and proceed
So, I would say in final,
will reopen tomorrow.
what's exciting about this is these observations now have given us this tail. These observations are now allowing us to be able to understand not only what's happening in 2015, 2016, but allow us to move forward in time to really begin to understand what is driving the carbon cycle and how, as people try to mitigate their carbon, the impacts of those carbons in the context of a changing climate. And I will just finish with credits, which will come right up. Thank you very much for your time.